Alright, hello everyone. Welcome back. Today we're going to talk about one of the A-level further maths pure component paper summation series. Now we need to write down an expression in terms of z and n for the sum of the series given here. Okay, once we have done that, we can use the De Moivre's theorem to deduce this particular relationship. Right, now that will be our questions today. Okay, let's take a look at how to work out sections number one. So we have 2n, zn. All right, now this is a more compact form of the summations of this series here. Now we're going to sort of elaborate this simplified notation into a more detailed um, representations of the summation of the series here. So we can write it down in such a way. Here you will have 2n negative 2. Oops, I think I used the wrong n here because we are trying to sum up to capital letter N here, right? So let's take a look at this. It's supposed to be capital letter N here. So let me correct that. So that should be N minus 2 here. So there'll be N minus 2, N minus 1 here. And then finally we have N to the power N here. Right. Now that's how it looks like in a more detailed structure. And then the best part about this detailed structure, even though it's lengthy, but we have more information relevant to this series here. So we notice that we can factorize this. So we can factorize this out. Now you don't really need to write the 1 though. Okay, become a habit now since I write it down as 1. Okay, that will be until we have here. All right, so there you have it. We can factorize it out. And then finally, okay, so finally from here, you have to sort of recall back any series that you are familiar with. So here we recognize that this is a geometric series with a common ratio given by the ratio between its two consecutive terms, right? So we recognize that. I'm going to write down at the side here. So we recognize that this is a geometric series. So this geometric series has the first term as a 1 in this case, and then it has a common ratio of you can work out the common ratio here, which is basically this divide by this. So that would actually give us a negative 1 z. Okay, so that's the common ratio. And then finally, don't forget the sum. The sum of a geometric series is given by a geometric sequence, to be precise, will be given by this minus 1, r minus 1 here. Now, given that in this case, I'm making assumptions that the magnitude of the common ratio is greater than 1 here, right? But for our exercise here, doesn't matter if you want to use the second form of the summation, which is this. Here we make assumptions that the magnitude of r is actually less than 1, right? So up to you which one you want to use. That's entirely up to you. It does not affect our result here, right? So next we're going to make use of this property here. All right, so we have this. Therefore, we have based on my initial selection, so there will be a 1 z to the power of n, because they are n term here, they are n term here, so minus 1 divided by. All right, so that's how it look like. And then we're going to do a bit of simplifications here. Now this one can be written as this, and then this one here is typically is this, um, divide by z divided by 2 minus 1 here. Right. So this is how it look like. And then from here, okay, if you like to simplify it by removing the 2 here, if you like, that will be this. And then divided by, if you multiply 2 here and the 2 the other side there, so we'll end up with this. Right. Now this one will be our final summations of this series here in its explicit form. All right. Now I hope that is clear. Next, I'm going to show you the relationship between this result that we are getting here as compared to the second part that we are trying to prove. So before that, I'm going to rewrite this for my reference. So that will be z divided by 2, n, subtract 1 here, and then divided by z minus 2 here. Now that will be our result. Yeah, one more remark I need to make here would be, don't forget the z is or can be written in its Euler form. Z is a complex number, so I theta, or it could be written in its argument form, so cos theta plus I sine theta here, right? So all these are a complex number, right? So those are the um, remark that I'm making for this summations or series, right? Stay tuned. I'm going to show you the next step, how we're going to use the Morse theorem to prove the following equation. All right, now we have successfully shown the expressions representing this series here, summations of this series. Okay, now next, I'm going to show you how to use the Morse theorem to actually prove the following equation here, right? Now it's a very lengthy journey that we're going to go through, so I'm going to show you step by step. And now the first step here is to consider. So here I'm going to consider consider this summations notation here. All right, consider this summation notation. All right. Now, knowing that the complex number z can be written in its Euler form or can be written in its argument form, right? Depending on the context, how you are going to prove that. So, at this stage, I will be using the argument form. All right, so I'm going to substitute that here. Would become cosine plus I sine theta raised to the power n here. Okay. So by using the Morse theorem, I can elaborate this or expand this into something like this based on the Morse theorem. Okay, and then there you have it. And then after that, usually for me, I prefer divide and conquer. So I will actually separate these two terms out. So I will have this one here. All right. Now, the main purpose why I want to split them out is because I recognize that this consists of the real component, and then it also consists of the imaginary component here, right? So now, of course, I can make use of both of them, right? to work out something, right? But based on the equation that I'm trying to prove here, it is making use of sign only. So therefore, I recognize that this component here is actually relevant to this imaginary section here, right? Therefore, therefore, this is one of the result that I'm uh, I'm expecting to make use of. So here, I'm going to make a few temporary result that I'm going to pay attention to proceed on with my analysis. So the first result, okay, these are the a very important result that you need to remember. Okay, based on the expansions that I have shown here. So from here, we know that negative n sine 110 n pi summation n equal to 1 up to n first. I'll try to put it as a n. Okay, this section here is the same as the imaginary. So I use IM to represent imaginary section of this summation series. So that is actually imaginary section of this. Okay, now you can see that there's a first result. To obtain this summation series, it is the same as the imaginary component. So all I need is just to extract these imaginary sections out. Okay, so just extract this out. And then now in this case, you will notice that the difference between this and this is, okay, there is a theta. So you recognize that the theta from here, I have to make a remark that the theta is actually pi over 10. If you compare the format here, there is a n, there is a theta, so the theta must be equal to pi over 10. Okay, so I hope that is clear at this point. Now I can make a few more remarks or result. Okay, so from here, we also notice that this one here, sine 110 n pi, instead of n, it is the same as the imaginary component of this Zn, where the n or the total terms in the series itself is 10. And then I have already made this remark, the theta must be equal to pi over 10. All right, so this is the main result that we're going to use to proceed on with our next analysis there. I hope that is clear. Okay, now next I'm going to show you how to actually apply the Euler form to work with the simplifications. Then we're going to finish up with the argument form once again, right? Okay, now I'm going to show you the next section shortly. All right, so I try to recap the result that we obtained previously. We have not done concluding this equation yet. Okay, so what we did previously was we found that this sine 1 over 10 n pi n equal to 1 n is the same as the imaginary parts of this summation series. Okay, sorry, let me correct that. Of this summation series to negative nzn up to 10 here, because this is up to 10. Yeah, correct. This is up to 10. So just let me put that 10 down. It's easier to recognize here. So therefore, the this left-hand side term is the summation of this series is the same as the imaginary parts of this summation series. Now we know that this summation series is the same as this. Therefore, we can also conclude that it must be the same as the imaginary term for this expression. All right. So the imaginary parts of this summation series must be the same as the imaginary parts for this expression here. So now we are going to look at how we are going to simplify this expression here so that we are able to extract the imaginary parts. Okay, now let's consider this. We have z divided by 2 n minus 1 here divided by z minus 2 here. All right, now as I mentioned before, I'm going to use the Euler form this time. So I'm going to make use of the Euler form instead of the trigonometry form to simplify it a bit before we go on to the final parts. Because if you look at the right hand side expression, it consists of trigonometry ratio there. Right? So this one can be written as I theta. Now there is also I theta. Yep, something like this. Minus 1. All right. So from here, all right. So there's a 2. Sorry, it's not a 1. So let me correct that as a 2. Right now, this is how it look like. Now, next, we try to simplify this a bit. So if I were to try to simplify this a bit, it would look something like this. Okay, I try to bring the 2 out. And then after that, I will have, okay, so in this case, I will have EI theta and then EIN theta minus minus a 1, is it? Did I did that correctly? No, I did not do that correctly. They're supposed to be inside there. Hold on. So there's supposed to be a negative n EIN theta minus 1 here. And then this is EI theta minus 2 here. All right, so I hope that is clear. Now the next part will be we are going to simplify this. Okay. Okay, how are we going to simplify this? The intention is to make sure that after we simplify, we will be able to obtain a real parts for our denominator. Right. To do that, we are going to rationalize this using the complex conjugates. Okay. To rationalize this using its complex conjugate, I'm going to introduce its conjugate here. So this is its conjugate. Okay. All right. Now after that, we're going to simplify this. Okay, I'm going to write it down somewhere here, so it's easier to refer to. From here, I will be able to get what do I have here? 1 minus 2 EI theta, 2 negative n EIN theta minus a 1. And then this part here, I will end up with, if you simplify it properly, you will end up with this EI theta plus E negative I theta here. Okay, so that's what we have at this point of time. And then next, we are going to expand the numerator here. So I'm going to expand the numerator so that I will have a negative 1 here, of course. Right? And then I will have a 2 negative n EIN theta. All right. So that's a negative 1, a 1 here. And then after that, I'll have a 2. All right. So that will be n plus 1. So that's n plus 1 like this. Okay. And then the E will be IN plus 1 here, theta. All right, just let me check whether I got it correct. Yep, correct. And then what do I have here? 1, 1, 1, 2, 3. Okay, 3. I'm supposed to have 4 terms here. So the last one will be a 2 EI theta. And then finally, I need to divide this by 5 minus 2 EI theta plus E negative I theta here. All right, so there you have it. This is how or the structure that I expect to have. You can see that I should be having some structure like this. All right, now I'm going to hold on here for a while. You can write out on your own. Now next I'm going to show you some small properties of the complex Euler form that we can make use of to further simplify this. Right? Stay tuned. Right? So I'll try to rewrite back into a shorter form. I have erased off the intermediate steps there. So this is the main result that we obtained in our previous section just now. All right. So what are we supposed to do? Now, of course, I'm going to show you little properties of the complex Euler form that we're going to make use of. Now, first of all, we know that z is equal to ei theta, which is the same as the cosine theta plus I sine theta here. Whereas z 1 over z here is e minus this, which is the same as cos theta minus I sine theta. Right now, from these two results here, we will be able to obtain the summations of this complex number would yield 2 cos theta here. Oh yeah, before that, I forgot to show you that. So the sum of this is basically ei theta plus e minus I theta, which is the same as 2 cos theta. That's the first result. And then the second result that we can get will be the difference between this will be e I theta subtract off e minus I theta, which is the same as 2I sine theta there. Right, now we're going to make use of one of these result that we can obtain from the properties of complex Euler form. So therefore, in this case, we will have n, and then this one here we can write as the cos. So this one here, okay, I just going to write it down at the side here so that you know what is going on. Ein theta can be written as cos n theta plus I sine n theta here. So therefore, this part here, I'll write it down as cos n theta plus I sine n theta. Okay, so that's what we have. And then next from here, we will have 2n minus 1. The same thing, cos n plus 1 theta plus I sine n plus 1 theta there. Right? So that will be a whole bracket here. And then, of course, we're going to add up the last part here. Right? So how that this is clear, I'm going to erase those so that it does not block our way here. Okay. Okay, so from here, I will continue on to write this. This one will be a cos theta plus I sine theta here. Alright, so that is what we have at this point of time. Okay, and then finally we have this cos. Right, this whole thing is 2 cos theta, so we multiply with 2 is actually a 4. So this one will be a 4 cos theta. Right. Okay, now you can see how lengthy that expression is at this point. Okay, but don't feel intimidated here, because we are going to recall back this very important objective that we're going to achieve. We are interested to obtain the imaginary sections of these rational functions here, right? So all you need to do is just collect all the imaginary term. Therefore, at this point, I'm going to write this one down here. I'm going to write down negative n sine 110 n pi 10 here. So don't forget the total number of sequence is 10, whereby the data is actually pi over 10. So I'm going to substitute this one directly into the equation itself so that it can ease my working here. So this whole thing is the imaginary section. Now we know that the denominator is a real part. So all we need to do is collect the imaginary sections for our numerator. So the imaginary sections will be, okay, so we will have 2 negative n, 2 negative n, that will be sine n theta, and then minus off with 2n minus 1, multiply with the sine n plus 1 theta, and then finally we have to have sine theta here, and then the whole thing is being divided by 5 minus 4 cos theta here, right? So I hope that is clear at this point. Right now, knowing that, okay, I need to remind myself again and again, this is pi over 10. So now it's time for me to substitute this in to here. So if I were to substitute this here, I will get, so if you look at the first term, that is actually a sine. So here I'll just write it down. So 2n sine sine pi. So 2n, yeah, 2n, okay, sine pi. Okay, so maybe I will try to rewrite this result up here so it's easier for us to see. Alright, so if I write it down here, it's a bit messy, so I'll try to reduce this here. Okay, I'm going to pause here for a while. You can see that the result is over here. So I'm going to copy this result up here because we no longer need this anymore. All we need to do is use this, and then by substitute the n equal to 10 and theta equal to pi over 10. And then we're going to check whether we are able to prove this or not. All right, now stay tuned. All right, here it is. This is the result that we have. Now we're going to substitute the n equal to 10 and theta equal to pi over 10 there. So therefore we will have negative n sine pi here, 2 negative n minus 1 sine, this one will be 11. Okay, so that will be 11 pi over 10 plus 2 sine pi over 10, and then divided by 5 for cos pi over 10. All right, now that's what we have. We know that this section here is 0 because sine pi is 0 here. And then there's one more remark that I need to write down here for your informations. Sine 11 pi over 10 is the same as sine pi plus pi over 10. That is the same as negative sine pi over 10. All right, so I hope that is useful at this point. So this part here is actually negative sine pi over 10. Therefore, we can simplify this as, because it's negative, so therefore it becomes 2 negative n minus 1 sine pi over 10 plus 2 sine pi over 10 over 5 minus 4 cos pi over 10. Right. So I hope that is clear. And then don't forget, the n is equal to 10 also, right? So I forgot to include that. So by including the n equal to 10, so there will be a 9 here. So there will be a 9. So there will be a 2 negative 9. 2 negative 9 sine pi over 10 plus 2 sine pi over 10 divided by 5 minus 4 cos pi over 10. And then of course finally you need to simplify this. All right, so that is a very easy simplifications there. All you need to do is just multiply by 2 to the power of 9 here to remove this. That will be 2 to the power 2 to the power 9 to the power 10, and then therefore you have 1025 here sine pi over 10 divide by, and then the last one here will be, if you multiply by 2 to the power 9 there, okay, so that is that will be 2560, and then let me see here, 512, that will be 2048. Yeah, correct. So that will be 2048. Finally cos pi over 10 here. So therefore, you can see that we have managed to prove that this summation series is the same as given as such. Yeah. So I hope that is useful to your learning here. I try my best to do it stages by stages so that you can see how the all these pieces can be combined to reach that conclusions there. Right. So thank you very much for watching. If you like what you're looking at, don't forget to subscribe and then click the notification bell to receive any latest video that I'll be uploading. All right. Thank you very much for watching.